Hello. Our paper title is Towards Designing Shared Digital Forensics Instructional Materials. My name is Deng. This is a collaboration project among University of Baltimore, Towson University in Maryland, and University of Missouri, Kansas City. This project is sponsored by the U.S. Department of Justice. Today, I'm gonna introduce the background of our paper, some important concepts in digital forensics, such as digital forensics artifacts, artifacts generators, and generator-based knowledge units. Then I will talk about the design principles we proposed for the digital forensics instructional materials. And at the end, I will go over some future works and conclude our paper. Recent reports indicate that cyber crimes have been increasing exponentially. So this leads to the significant need for digital forensics experts. So local, state, and federal law enforcement, they all depend on digital forensics professionals in the investigation of cyber crimes. From 2016 to 2026, the demand for digital forensics related jobs is expected to grow by 28%. In other words, which means more than 28,000 jobs will be added. And digital forensics professionals, they are people who can help in the recovery and investigation of digital evidence. So they need to have in-depth knowledge and solid experience in cyber investigation, and also be able to present and explain digital forensic evidence in court. So as educators in this field, we do feel that there are several major barriers to digital forensics education and to practice cyber investigation techniques and skills. For example, we do not have enough experienced educators in the field, and we do not have enough publicly available hands-on digital forensics instructional materials. To the whole digital forensics education community, these are significant challenges and we need solutions for them. And the goal of cybercrime investigations to provide, to prove whether a suspect is responsible for a crime by reconstructing the crime scene. This figure shows an evidence-driven approach to reconstructing a crime scene. It shows the traceability among a set of fundamental concepts used in the cyber investigations. A suspect performed some crime activities, and these activities apply to certain digital devices and generate artifacts, and devices are part of IT infrastructure. And this infrastructure also generates different artifacts. And these artifacts become evidence for cyber investigators to use to reconstruct the activity and the crime scene. So here we provide some formal definitions to these fundamental concepts. So we define digital forensic artifacts as any type of items produced by a digital device stored in an electric form and used for forensic investigation. They are byproduct of a suspect activity and when using digital devices. And common digital artifacts include maybe work documents, pictures, applications, network traffic, and logs. Identifying digital forensic artifacts relevant to a crime is the first and the fundamental step of digital forensics investigation. Next, we define digital forensic artifact generator. They are hardware or software that generates digital forensic artifacts. For example, when a file is modified by a user, a corresponding operating system will generate the last modified timestamp and record it in its file metadata. Here, the file is a digital forensic artifact, and the operating system is a digital forensics artifact generator, DFAG. We classify digital forensic artifact generator into the following categories: computer, server, mobile, and IoT devices, networking devices, operating system, and application. Then we define digital forensic evidence. They are digital forensic artifacts that is presentable for the purpose of proving a crime admissible at the court. And there are properties associated with the fundamental questions related to cyber investigations, such as who the suspect is, when an incident happened, what and how it happened. To answer these questions, the properties of evidence must include the artifacts from which evidence was extracted, evidence timestamps, devices, and activities that generate the evidence, and the tools that used to obtain the evidence, and the investigator who analyzed the evidence. Next, we introduce digital forensic artifact generator-based knowledge units. A knowledge unit is a thematic collection that includes several related educational topics. The concept of knowledge unit is widely adopted by the Center of Academic Excellence, CAE, sponsored by NSA. We use knowledge units to outline major topics and learning outcomes in their instructional materials, aiming to optimize the clarity, straightforwardness, and conformity. In our research, we consider DFAG defines what artifacts will be generated, and knowledge unit defines what artifacts need to be covered in the instructional materials to perform investigation tasks. There are two types of DFAG-based knowledge units. The first one is device-specific knowledge units. They are derived from the hardware of DFAGs, such as computer forensics, server forensics, mobile and IoT forensics, and network device forensics. And another one is domain-specific knowledge units. They refine device-specific knowledge units to knowledge domains that cross-cut all devices, including media forensics, memory forensics, operating system forensics, software forensics, and network forensics. CAE-CD implicitly defines two device-specific knowledge units. They are host forensics and device forensics, and two domain-specific knowledge units. They are media forensics and network forensics. And each knowledge unit is specified using the following pattern. The pattern is the intent of the knowledge unit name. A knowledge unit is to provide students with the ability to apply forensic techniques to investigate and analyze the DFAG of the knowledge unit. So for example, for host forensics, it is the intent of the host forensic knowledge unit is to provide students with the ability to apply forensics techniques to investigate and analyze a host in the network. And the table on the right compares DFAG-based knowledge units and knowledge units defined by CAE-CD. We make the following adjustment. We split host forensics defined in CAE-CD into computer forensics and server forensics. And we change device forensics to mobile and IoT forensics. And we also add more memory forensics, operating systems forensics, and software forensics. Next, in our paper, we propose several active learning-oriented design principles for instructional materials. And our goal is to infuse active learning into the design of our materials. And that way we can enhance students' learning experience. So I will introduce them one by one in the next few slides. The first one is real-world scenarios. We believe that real-world case study is an effective way to define the objectives of digital investigation and boost students' interest. The table on the right shows 9 real-world cybercrime cases used in the instructional materials. Each case study consists of a list of labs. For example, the first one, NIST data leakage, it includes 14 different labs. And the disk and the memory involved in these cases are acquired, and we made it publicly available on our GitHub repository. The second principle is comprehensive labs. A comprehensive case study is essential for students to experience all the phases of digital forensics. So the table on the right shows the P2P data leakage case study with 11 different labs. The case study mainly covers 1 device-specific knowledge unit and 4 domain-specific knowledge unit. Topics covered by the case study are range from the lab environment setting up, disk image acquisition, disk media analysis, to the reconstruction of the timeline of the crime scene. Next, we also utilize a problem-driven approach to design labs. The problem-driven approach allows students to provoke reflection, to mobilize attention, and to promote targeted and context-sensitive engagement when conducting case studies. So for example, update sequence number USN journal can be used for reconstructing users' behavior. We design questions in our labs to guide students' activity, such as what is the USN journal, where is the journal located, so students can use the questions to drive their lab. Next principle is self-paced learning. It enables students to customize their learning based on their diverse backgrounds so that their individual study needs can be fulfilled to the utmost. For each question proposed based on the problem-driven approach, we provide solutions with a detailed explanation, including theory, including tools, commands, and instructions, and screenshots of solutions. The figure on the right shows an example of visualized instructions to different operations. Visualized instruction provide repeatable and intuitive solutions to help students with diverse backgrounds to learn at their own comfortable pace. The last principle we consider an integrated open source lab environment very, very important. All digital forensic labs are hands-on intensive and rely on many open source tools. But installing these tools is very time-consuming and error-prone. So we have built our digital forensics platform based on Kali, and also designed 2 different approaches for students to set up the lab environment. The first one is they can import our customized Kali virtual machine image with all the necessary open source tools pre-installed in the virtual machine. The second one, students can install open source tools in Kali by themselves using the shell script we have developed for them. There are 3 different types of investigation tools, including in the virtual machine we provided. They are tools provided by Ubuntu. They are tools included in Kali, and also we include tools needed to be recompiled and installed for cyber investigation. And the screenshot on the left shows the execution of customized shell script to install the 3rd type of tools, and the table on the right shows a tracing table that maps among labs the artifacts to investigate, and Linux tools and commands used to investigate artifacts in our case studies. And we have developed the instructional materials and shared them on a GitHub repository. The figure on the left provides an overview for contents of the materials, and the figure on the right shows that our repository has been visited and starred many, many times. It's also being shared through many social media websites such as Twitter, Facebook, and LinkedIn. Overall, to summarize our work, we provided a fundamental understanding of how digital evidence is generated and what to investigate. We developed scenario-based and problem-driven hands-on labs with visualized solution guidelines for self-paced and enhanced active learning experience. We also created an integrated Linux-based investigating environment so that students can practice labs and learn digital forensics and cyber investigations. And we published instructional materials on a GitHub repository so that everyone in the digital forensics community can share, can use, can contribute. For future work, we would like to design more and more real-world case studies, and we also plan to introduce formal evaluation and collect feedback from students and faculty. We will also formalize evidence so that we can better share digital forensic evidence with community. So that's our paper. Please feel free to contact us if you have any questions or comments. Thank you very much.